the second part of this lecture, I will in principle only repeat stuff that I think you should have seen. If you haven't seen any of that, then I think that might be a bit difficult, then please let me know. So I expect people haven't seen an introduction to logic and propositional logic, and so this is more repetition so that we are on the same page, and then tomorrow we get into how to use this for our practical problems and how to do more automated reasoning with this, so which I think is new material, but in a way this should be familiar. So if this is not familiar, then let me know afterwards, or and I will point you to some material. So as I said, logic is the generic formalism that helps us getting from some explicitly stated sentences and a knowledge base, so to speak, to some implicit new facts. And the technical notion to that is entailment. So we want notions such as safety or battle strategy to follow from the logical notion of entailment. And for that, we have a formal system that is a logic, in my view, defined by three elements. The first one is we need a syntax. We need some way of writing down unambiguous sentences in our formal language. We need a semantics, which is to assign meaning to these unambiguously stated, formulated sentences in our knowledge base. And we need a calculus, a machine that tells us whether something is true or something is entailed, given this language and the intended meaning that I wanted to have. Yeah? So these are the three elements that, in my view, always constitute a logic: a syntax, a semantics, and a calculus. And so syntax defines what the legal expressions are of the language, so the well-formed sentences in my language. The semantics says what they mean, and basically you give some meaning to the sentences via the notion of interpretation and models. And then based on this meaning, you have also notions of what can be derived. And finally, you have a calculus to calculate, actually on a machine, automatically determine the meaning for those legal expressions. And we're going to move to propositional logic, but just to make sure that you understand that this is more generic than just those classical logical approaches, we have the same, if we talk about arithmetic, for example, we have a definition of what are the valid sentences of this simple arithmetic language with equality. So we have variables, operators, and numbers on the left-hand side. We have a comparator in the middle, and we have a variable on the other side. So that would be a valid sentence, valid inequation. Whereas this statement, x2 plus y, is not a valid sentence. So it doesn't give us a yes-no meaning. And that's a definition of the language. We assign now here some kind of truth value to one of those valid statements. It wouldn't make sense to define a truth value to this statement, x2 plus y, has no notion of true or false. And for example, we can, if we say we can assign some values, our interpretations of the world are just assignments of values to variables, then this statement, x plus 2 is smaller than x plus 3, is always true, no matter how we choose x from the domain of numbers. Yeah? So that's a sort of truth with respect to all the worlds. It's a semantic notion of validity, as we will call it later. And other are always false, or other sentences in this language are true with respect to some interpretations of the values and false with respect to others, like the last one here. And then we can assign values true and false to those statements in our language according to the simple rules of arithmetic that we all know, to the algebra that you would apply in calculating whether this is true or whether this is false. So the notion of a logic goes beyond what you know with propositional logics or first order logics, but also to formal systems more generally. Whenever you have a formally defined language, restricted set of sentences to which you assign a formalized meaning, and an algorithm to find out whether what the meaning is of your intended sentences. And now let's apply that to the more standard language of propositional logic that I believe you're all familiar with. Let's do exactly the same. Let's start with the syntax, then the semantics, and the calculus. I will spend all of Wednesday on to show you 2 different or 3 different calculi in order to calculate whether a statement is true or false in propositional logic. For now, it's only about what language do we have and what does it mean. And obviously, we do this here because we want to use propositional logic for modeling and later also for reasoning in the domain of Schnapsen. It can also be used as an example for the Wumpus word later in the lecture. So let's see what are the valid sentences, the well-formed sentences of our logic. We have propositional symbols, so that's the induction basis of the induction. We have a set of symbols to which we want to assign values true or false, and that's called our proposition. It's raining, the room is full, my name is Stefan, and so forth. Things that you can assign a value true or false. And then whenever S is a sentence, then negated S is a sentence. So we're now moving up the inductive definition. And we introduce the operators conjunction, disjunction, implication, and equivalence. If you are strict, you only need 3 of them, but this is what you use most of the time. And this is our way of defining unambiguously the language of propositional logic. So these are all the sentences in propositional logic follow this definition. And in principle, we're done now defining the syntax of the language. Just to make it a bit more difficult for you and sort of more realistic, there are about 73 up to I don't know, infinitely many ways of writing the same language. So sometimes we use this symbol, sometimes it's written like this, just a separator line. Sometimes it's written like this, X or Y. Sometimes it's written in this form. And these are just some syntactical variants of the same thing. You have the same for negation. Sometimes we find it like this, sometimes we have it. There are many, many different ways of writing this down, and I ask you not to be confused if I sometimes use different of those operators just to write down the same things. Now, when I have my unambiguous language, maybe with some sort of different use of symbols, but that's really just a rewriting thing, then I want to assign a formal meaning to my sentences. And the trick about these sort of logical languages is that as soon as we agree upon the language itself and the meaning that we want to assign to these languages, then we have the notion of predictable inference. So if I give you a set of facts and the language in which it is written, and I give you the same set of facts and the language it's written, you should have exactly the same things to say. So there should be no difference in interpretation. And that is not trivial, because even in database systems which we trust, they all have their own way of returning results. So some of them have a cutoff at 1,000 results. So if you might not even know, but you get different results from different systems. And in logics, we try hard to understand the systems so well that you always get the same results when you ask your queries. So it's about predictable inference, and we're now defining the things that you can derive from a given set of facts from a knowledge base. And we do that, so we take care in principle of a notion of truth. But philosophically, this is very difficult. We use a very technical definition of truth here. And we do that by the notion of a model. And a model is basically a formal interpretation of the world with respect with respect to this one, we can define also a notion of truth and evaluate whether something is true or not. And in principle, a model of a sentence is an interpretation of the variables that holds for all the constraints of my knowledge base. And that is then the model M of alpha is a set of all the models of A alpha. And with respect to those models, so all the possible interpretations that are consistent with a given knowledge base, we will later define notions such as validity, entailment, and so forth. Yeah?
On interpretation, indeed, we actually use our course on propositional logic. We use the vertical bar as the shepherd stroke. It was not an analogy with the OR function.
This one. Yeah. That's one of the big problems in.
Now you will use it as a
disjunction.
Same way as a
disjunction. Yeah. But you'll always encounter these sort of symbol overloading that everybody has their own. You need to define first what do you mean with a certain symbol. So that's going to be a problem further on. Basically, this notion of model, which I will get into more in a couple of minutes, is very important because in principle it's all the possible interpretations of the world that are consistent with our knowledge that we have modeled in the knowledge base. And this is the definition which we use in order to define our notions of entailment, for example. So the knowledge base entails a fact alpha if alpha holds in all the worlds, so all the models in which the knowledge base is true. So we have the knowledge base that is interpreted in some way, and if whatever way I interpret my knowledge base, some facts are true, then we call this entailed. So let's see how this would work in our interpretation of the Wumpus world, and why this is useful for us to make these conclusions that we've just made sort of intuitively, because we didn't have any formal grounding for what we decided. So we are in the situation that we've been in 1.1, moving right breeze in 2.1, and now let's look at these situations where we don't know anything about those three fields here, and basically we want to know whether there are any pits in any of those situations, and whether basically one of those fields is safe or not. What you basically then do is for all so we only look at a very restricted sets of things that we can interpret here, so only at those 5 fields in the game, and our possible models are that we have a pit here, a pit here, a pit here, a pit in these two, a pit in these two, a pit in these two, and a pit in all 3 of them, or no pits. So basically we have 8 different possibilities for having a pit here or having no pit here. Yeah? And these are all the possible interpretations of is there a pit or is there not a pit, and this is all the possible ways of looking at the game given the information that we have when we've just moved to 1.2. And now the question is there anything that we can derive on the basis of this being all the possibilities that helps us making decisions according to the semantics that are now defined for this logic? So basically, which of those 8 worlds are consistent with the Wumpus world as we've played it so far? It's only the red ones, yeah? Because if this is a smell, then somewhere here around there would have to be a pit. This is a breeze. I apologize. This is the breeze. So if this is the breeze, because the breeze is what we have observed, so this is what our knowledge tells us about the situation. So we have the breeze in 1.2. And now which of those worlds, these 8 interpretations of the world, is consistent with this assumption, with this smell, or sorry, the felt breeze in 1.2? This one is, because there is a pit, at least one pit in an adjacent position. This one is, but none of the other 5 is consistent with the rules of the game that if there is a breeze somewhere, then there must be adjacent the pit. Yeah? Because this is on the diagonal. Yeah?
Is that because the knowledge base is made by only the current assumption I can make, given the current thing, not previous?
No, this is because, because of the information that we have, because of the knowledge that we have gathered in the previous stages of the game.
Okay, so
and
why not the right part also?
This?
Top right, yeah, also that one.
Because we have been in 1-1 and there has been no breeze.
Okay, not that one maybe, but the second one. The third one?
This one?
No, the right.
This one? Yeah. Because there can't be a pit here, because otherwise there would have been a breeze here. Here it should be, we haven't noted a breeze here, so there can't be a pit here. Yeah? So these 5 situations to the right, they violate one of the assumptions of the game that we have defined. Yeah, is that clear? So basically, in all the interpretations of is there a pit in one of those 3 fields here, 5 of them are impossible if it's consistent with the games of the rules of the game. And only those 3, the red ones, are basically possible situations. And now we can look at all those possible situations and find whether there are common patterns in those, and the things that are true in all those 3 models. These are the things that follow from our knowledge base logically according to the semantics of the model theory. So the entailment was defined as, so we write it down like the knowledge base, here is my pointer. The knowledge base implies some facts that if some information holds in all the models of the knowledge base. So let's look now. Whether, for example, the statement 1, 2 follows from the knowledge base. So that was our assumption that we had here on the board. We want to find out whether safe 1, 2 is entailed, is true with respect to this knowledge base. And now we have the logical notion here with the question, given the knowledge base of the Wumpus world rules plus the observation that we had being in 1, 1 and in 1, 2. And the question is now, is 1, 2 safe? Or in other words, is 1, 2 safe entailed by the knowledge base? And basically now we look at all the statements in which this is true, 1, 2 is safe, this is the yellow line, and we can check whether 1, 2 is safe, and it actually is, because in none of the interpretations in which 1, 2 is safe holds, because in none of the models of the knowledge base, this does not hold. Yeah? Yes?
At this point, I'm already in 1, 2, right?
Yes, you are in 1, 2. Yeah.
Right, so 1, 2 is safe. Isn't it evaluated when I'm in 1, 1?
You could probably evaluate one step before, but you can also evaluate here by just looking at all the models of my knowledge base, and to see that in all those models of the knowledge base, it basically is safe. Yeah? You do this basically by checking whether the red circle is a subset of the yellow circle. Here is another way, another question, and that is now, is 2 safe? And what you do is you look at all the models of your knowledge base, and you look at all the possible interpretations in which 2 is safe. And that would be this one, this one, this one, this one, this one, and this one. And basically you can see that this is not the case, that because not in all the models is 2 Wait a second, now I'm confused. These two models are not in this dotted line. And basically these two models violate the assumption that 2,2 is safe. Yeah? Can you see that? So you have to check for all the statements in which the knowledge base is true, and you have to check whether it's a subset of the set of all your safe, the ones where 2,2 is safe. So the algorithm, the definition of some facts being true with respect to the given knowledge is always look at all the models, which is the ones here in red, and is a statement true for all of the statements that you want to prove. Here I want to prove that alpha 2 is true, which means that 2,2 is safe. So there is no pit here. And you see that there are elements, possible interpretations of the world, basically, that are consistent with my knowledge base. And in these two situations, 2,2 is not safe. So it violates the definition of entailment. So I've got the impression that I've managed to explain this very simple fact in a very complicated way. So if you look at the slides later on, I believe that it is really easy to understand. I will move on because I don't think I can make it any easier for now. But if you look at the slides, it really is a very, very simple definition. Namely, a fact is true if all the interpretations in which satisfies it is a subset of all the interpretations that are models for the knowledge base. And this is a graphical way of looking at it. You just have to check whether the red states interpretation of the world are a subset of the yellow ones. And in this case, this is the case. So you can derive the fact because of this subset relation between the interpretations of the states. And in this in the next case, you cannot establish this subset relation. So it basically means the opposite is true, that there are some models, namely these two, for which the statement is not true. And that's all there is to it. So it really is far more simple than I made it appear to be. And based on this definition, we can now sort of build up a powerful vocabulary of what you can do with these logics, namely define the notion of entailment. A sentence alpha is entailed by a knowledge base if and only if alpha holds in all the models of the knowledge base. And based on this notion of entailment and models, we can also define a notion of validity. So if something is true in all the models of a knowledge base, then it's called a tautology and it's called valid. And basically an example in propositional logic is the statement true, which statement true is always true in all the interpretations, but also A or not A. A implies A. In these kind of statements, you cannot find an interpretation for the propositional variable A that makes the whole formula true, falsely interpreted. Simply impossible to do so. In that case, you call it tautology or valid. If there is a model, then we call the formula satisfiable. And if there is no model, then we call it unsatisfiable. These are some classical notions, and they are all based on this definition of propositions, of models and in propositional logic. And how is this defined then to the individual formulae? We can assign arbitrary values according to a certain interpretation to our propositional variables. So these variables, you might recognize them, they are already from the Wumpus world, is just some arbitrary assignment of a value true to be 1, 2, which we would assign to the value there is a pit in 0.12. P22 would be a pit in 2.2, or a P31 in this interpretation of the world would not have a pit in 3.1. So we have the propositional variables, and we interpret them in one way or the other. And then we extend this notion of truth for the truth and falsity for a more complex formula in an inductive way. So if S is false, then not S has to be true. If S1 and S2 are true, then the formula S, the conjunction S1, conjunction S2 must be true, and so forth. So that's a standard way of just porting the truth of individual propositions or more simple propositional formula to more complex formula. So it's the compositionality of the propositional logic here. And that basically the other way around. Once you have a formula such as this one, and you know you have an assignment of values, so one possible interpretation, you can also assign unambiguously a value to the entire formula. So here we have a complex formula, not P12, and then the disjunction between P22 and P31. And we have the possible assignments up here, true, true, and false. And then we can simply evaluate the value, the truth value of this formula to being true in this specific case. And then based on these semantics that I just showed you, there are some equivalences that you can prove to be true. And they are very powerful because we can later use them as rewriting rules when we really actually do automatic reasoning and calculation with them. And in the exam, I will give you a sheet of those so you don't have to learn them by heart. But in principle, they are all sort of semantically, logically, they follow automatically from the meaning of those operators. And they allow you to transform formula into a simpler formula and then calculate the truth value of those. So let's make the step back now to the Wumpus world, where we have statements about. So this is one way of modeling the Wumpus world. There could be different ones, there could be other ones. So PIY is meant to say that there is a pit in square IY. BIY is true if there is a breeze in IY. So that's the intended meaning. And then we have statements such as not PI, P11, not B11, B21. And that's exactly the kind of language that I used for our motivational example. And then we can, in this language, define the rules of the game. We can, for example, say that if there is a breeze in 1-1, then this is equivalent that there must be a pit in 1-2 or in 2-1. So basically, remember that we're still in this little corner down here. And so if we have a breeze 1-1 here, then here must be a pit and here must be a pit. Yeah? That's all it says. Or, so either here or here. Yeah? So this is the situation. And if we have a breeze in 2-1, this one, then either here or here or here. Yeah? And if we're in the middle of a field, we would obviously have to model all four around. And we can define these rules for the pits and the breezes, and we can define those rules for the stink and the Wumpus, and for the errors, whatever, you can define complex rules for this. But basically what it all comes down is that you now can do formal reasoning and check specific things. For example, safety of a certain place, the fact that there is no Wumpus, the fact that there's no pit of a state. You can simply just check by entailment, logical entailment, when you have a complete representation of the game rules, and apply a theorem prover to tell you whether the position is safe or not. The good thing about it is that propositional logic is declarative, so you can write down those rules explicitly, and you can check them. We as human beings can check them, We can improve them, we can add more rules if we want, we can adapt them, and we can talk about them. And in many of the implementations of these games, you cannot do that. Or even if you write a computer program where you sort of intrinsically model all those rules of the games, that becomes already quite intricate sometimes. So this is really nice to have this property of explicit declarative definitions. We can also model negative things. So there is no breeze here. The compositionality, so the properties that if we know something about individual fields, tells us something about combinations of information over different, for example, different places in the field and so forth. And the meaning is always the same. When we have this definition, we have a knowledge base, we have propositional logic, and we apply a reasoner, it should always give the same results. So there's no impact from outside, so there's no context dependency. Very different to natural language processing, where sometimes you don't know how to interpret things, how to interpret rules, and so forth. So we are in the field of unambiguous decisions here, so that's quite nice. But the big problem that we are going to see, we spend most time tomorrow on it, is that the expressive power of this language is limiting what we can do here. And there are two things. The one thing is it's incredibly tedious to write down all this information. That's the one thing. And we can't really relate all the different properties of the game to each other in this very simple mechanism. So we see this best when we talk about Schnapsen, but it's maybe good to also go back to this example here. The big problems with the representation in propositional logic, because what I've shown you here is the definition that if there is a breeze in 1-1, there should be a pit in one of the adjacent fields. Yes? If I want to model this in propositional logic, how many of these statements do I need for the simple Wumpus world?
I would say 4, but I'm not sure. I would say 4, but I'm not sure.
4 more. I want to give more. 16, I would say.
Yeah, I would say one for each cell.
Exactly, one for each cell. I have to say, is it? So I would need 16 cells telling me that an adjacent field to a breeze one of the adjacent fields of a breeze must have a pit. And that is one statement in a more expressive language that I just gave you. But if you want to write this down in propositional logic, you have to write it down for each of the fields. And you have to do that for each of the properties in on all these 16 fields. That basically means that if you want to even the simplest rules of breezes, pits, and wumpuses and smells, you need 16 times the number of interesting facts that you want to add in your knowledge base. And that is very tedious. And if we now move to the Schnapsen, then basically we have a very similar situation. And I've written down a rule here for a trump wedding played on one specific card. And that can be played if the specific card is a queen, and if it's trumped, and if there exists something with the same color, which is a king, and which is on my hand. Yeah? So that's one way of saying, okay, I can now play a trump wedding. These are the constraints for me to play a trump wedding. And this is very elegantly written down here, if you can write it down for all the X, for all the cards in the pile. But now I have to write it down for all the 20 cards that I have. And for all the 20 cards, the 20X, I actually have to add another 20 times the statement, because it could be any of these Y. So in order to write down this statement already, I would need a lot of statements in propositional logic.
So
Yeah?
Shouldn't I follow the conditions I have? So I shouldn't just look through all the cards I can have, all the other couple I can have, but only the one that satisfies being a Q and a trump card.
Yeah, so it comes down that in your modeling of the game, you say that you only have 4 queens.
Yes.
But the question is, what comes first? So do you want to type your cards first with being a queen and being a diamond? Or do you want to explicitly model that in the language? And of course, you're right. If you model this more cleverly, then you would probably take some kind of typed first order logic and translate it into propositional logic efficiently. But we'll look into that a bit more tomorrow. Of course, for the modeling of these languages, what you could also do is move to first order logic. And first order logic is exactly this language where you can make quantified statements over all the possible objects in the domain. And basically the trick we're going to apply is that if you know that your domain is finite and you only have a finite set of domains, like we have with a finite domain of cards and a finite domains of square, then we can always translate back into propositional logic, but we're going to model our properties in first order logic. That's the trick that we're going to apply. So what was first order logic again? Propositional logic assumes a world containing of facts, something that is true or something that is false. These two options you have. In first order logic, now we have different types of things we talk about in the world. We talk about things that are objects, that are relations of objects, and that are functions over objects. Yeah? So in a way, we also apply different things to that. So we're not interpreting our facts as true or false anymore. We're interpreting them as things in a domain and relations between things in a domain. So we can talk about people, houses, numbers, colors, and so forth. Relations, something's being red, something being round, brother of, and we can talk about values that we assign to those, father of someone, and so forth. And that gives us a far more powerful representation language in which we can write down those things in, for our games, far more elegantly. So these are the kinds of statements we could make before we do the composition. So we have constants, King John, the number 2, and so forth. We have predicates, so King John is a brother of. We have functions, the square root, the left leg of someone, and so forth. We have variables that might be instantiated with objects later. We have connectives, so the operators. These are now the same operators that we've seen before in propositional logic. We might have equality, and we have definitely quantifiers, the universal quantifier and the existential quantifier, where we can make statements over all the possible interpretations for a specific variable, or for a specific one, that there must be a specific one. So the definition again is now, we start not only with propositional variables, but we start with atomic sentences, and they can be either predicates, so binary, unary, and so forth, or terms, equality between terms, and a term might be a function, or a constant, or a variable. So we can say things like the brother of King John is Richard Lionheart. We can make statements that the length of the leg left of Richard is bigger than the length of the left leg of King John. These kind of statements we can now say in this language. Of course, this makes it far more powerful. And when we have our sentences, we can use, again, the standard quantifiers, the standard operators, so negation, conjunction, disjunction, like we did in propositional logic, but now we can also apply those quantifiers, universal quantifiers, existential quantifiers, so that we can now say that if King John and Richard are siblings, then they are also siblings in the other direction, and we can make statements that if 1 is smaller than 2, this statement is true if 1 is smaller than 2, or 2 is bigger or equal than 1. And these kind of statements about relations between objects in our domain. And truth is now defined in a very similar way by defining sentences to be true with respect to a model, where the models are now objects in relation to those objects. So they are not interpretations of values to variables anymore, but they are now graphs, basically, where you have objects and relations. And for the constant symbols in our language, we assign object values. For the predicate symbols, we assign relation values. And for the function symbols, we have functional relations in our model side. And the definitions of entailment remain exactly the same. So now we would interpret a sentence about, or a set of sentences, a knowledge base about these objects. We would interpret them into these kind of graph structures where we have objects in the domain that are related by relations, and that the function of the left leg of, so these double lines there would be functions on specific objects. So this is now the interpretation of the syntactic representation of the words we have. And the two remaining things before we leave it for today are then the quantification, where we can say universal quantification, then we have a set of variables and a sentence, and then these variables are applied over sentences, such as sentences like everybody at the US government is smart, which means that for all x, if you are x US government, then would imply that x must be smart. These kind of statements are the ones that you can now do with quantification. And the definition of the semantics is then for all x, p is true in a model, if p is true, with x being each possible object in the model. So you just choose all the models and you check whether they are true in the models. And the second one is the existential quantification, where you would be able to represent that there is someone smart in the US government, so they exist in X, it is at US government, so it combines two objects basically with the at relation, and this object X must have the smart property, and then the definition is of the semantics is again, exist X P is true in the model, M if and only if P is true, with X being some possible object in this model. And these are basically the definitions of the operators, universal quantification, extensive quantification, which are very powerful in modeling these properties of the games, for example. And we're going to talk about that tomorrow. So thank you, and see you tomorrow.